The objective of this lecture is to provide an introduction to work and energy for a particle. The starting point for this lecture is as follows. The kinetic energy of a particle P of mass m is defined as T is equal to 1/2 m VPI dotted with VPI, where I is an inertial reference frame and VPI is the velocity of point P as viewed by an observer fixed in reference frame I. Now the basis for this lecture is going to be to take the rate of change of the kinetic energy. So the rate of change of the kinetic energy is given as d capital T dt is equal to d dt of 1/2 m VPI dotted with VPI, which is equal to 1/2 m d dt of VPI dotted with VPI, because the 1/2 and the m are constants. And that, because the scalar product of Vp and I with itself is a scalar, I can take the rate of change in any frame. So this becomes 1/2 m ddt in I of Vpi dotted with Vpi, where the rate of change has arbitrarily been taken in reference frame I. And that's equal to 1/2 m, and then if I take the rate of change using the product rule, I get the acceleration of P in I dotted with Vp in I plus Vp in I dotted with the acceleration of P in I. But the scalar product is commutative, so as a result I get 1/2 m times 2 AP in I dotted with Vp in I, which is equal to the mass times the inertial acceleration dotted with Vp in I. So then, applying Newton's second law, that is, applying F equals MAPI, gives that the rate of change of the kinetic energy is equal to F dotted with Vp in I, and this result is what's called the Work-Energy Theorem. Now you can see that from this result, it says it provides a relationship between the rate of change of the kinetic energy to this quantity F dotted with Vp and I. The quantity F dotted with Vp and I is called the power of the force F. So therefore, the work-energy theorem states that the rate of change of the kinetic energy of a particle of mass m is equal to the power of the resultant force acting on the particle. So from this we can actually define other quantities that we can use in relation to the rate of change of kinetic energy. In particular, we can define the work of a force. So this leads directly into the concept of a work of a force. Now, this applies to any force, but we're going to ultimately relate it back to the work-energy theorem. So we're going to start with just a general force. So we say let F be a force acting on a particle P of mass m. Then the work done by F on the time interval t in t1 to t2 is defined as W t1 t2 is equal to the integral from t1 to t2 of F dotted with the inertial velocity. So you can see that the work done by the force is equal to the integral of the power of the force. So therefore, the work done by F on t in t1 to t2 is the integral of the power of F from t equals t1 to t equals t2. Now suppose that F is the resultant force acting on the particle. So what we're going to do is we're going to just change this now. Instead of F being a generic force, we're going to say, suppose that F now is the resultant force acting on the particle. Then we know from the work-energy theorem that the work done from t1 to t2, which is now equal to the integral from t1 to t2 of F dotted with Vp and I dt, where F now is the resultant force acting on the particle, is equal to the integral from t1 to T2 of the rate of change of the kinetic energy. So therefore, the work done from T1 to T2 is then going to equal the kinetic energy evaluated at T2 minus the kinetic energy evaluated at T1. This is what's called the principle of work and energy. It's also called the principle of work and kinetic energy. It's the principle of work and energy. And it states that the work done on the time interval from T1 to T2 of the resultant force acting on a particle is equal to the change in the kinetic energy. So let's write that down. So the principle of work and energy states that the work done by the resultant force acting on a particle P of mass m on the time interval T in T1 to T2 is equal to the difference between the kinetic energy at T equals T2 and the kinetic energy at T equals T1. So now, from these two results, we're actually going to start specializing a little bit in categorization of forces, and then we're going to actually talk about conservative forces after we categorize forces. So categories of forces. So these are broad categories of forces, but they provide a way to be able to do the next step, which will be to deal with with what's called total energy. So the first are what are called non-conservative forces. And the second are what are called conservative. Now, non-conservative forces don't really have any particular structure, but conservative forces do. So we're going to actually talk about conservative forces. So a conservative force, so a force, F superscript C, is said to be conservative if F sub C satisfies the following relationship. Satisfies the following condition. That F sub C, or F superscript C, is equal to minus the partial of U with respect to R, which is equal to minus the gradient with respect to R of U of R, where U equals U of R is a scalar function of position and is called the potential energy of F C. Now, it's important to note about this position. It is important to note that the position R is the position of the particle relative to a point O fixed in the given inertial reference frame I. In other words, we say that R is equal to RP relative to O, where O is fixed in I. Now, this can be true for any inertial reference frame, but I defined the inertial reference frame, or I noted the inertial reference frame was I, so that's why this particularly pertains to this reference frame I, to which I started at the beginning of the discussion. So now what we can do is we can actually start using this relationship to be able to build upon it, to be able to define more properties of conservative forces. So using the definition of a conservative force, we can now develop an expression for the power of a conservative force. So for starters, I should say to start, we know that the power of a conservative force, or power of a force, is given as F dotted with VPI. That's the power of F. So that implies for a conservative force, F superscript C, the following is true, that FC dotted with VP and I is equal to the power of FC. Now, we also know that FC is equal to minus partial of U with respect to R. So this says that minus the partial of U with respect to R dotted with VP and I, that's equal to the power of FC, and that's because FC is equal to minus the partial of U with respect to R, which is what we already described. Now, we also know that the rate of change of U, because U is a function of R, is equal to the partial of U with respect to R dotted with dr dt in I, where I've arbitrarily taken the rate of change in reference frame I because U is a scalar function. So now we actually can write the next result, which is that because R is equal to RP relative to O, and O is fixed in I, we have that du dt is equal to the partial of u with respect to r dotted with vp in I. And that's because vp in I is equal to d dt in I of rp relative to O, which is also equal to dr dt in I. Now, from that, we can actually write, and you can see that minus du dt is equal to minus du dr dotted with vp in I, which is equal to fc dotted with vp in I, which is equal to the power of fc. So, therefore, the power of a conservative force is equal to the negative of the rate of change of the potential energy of the conservative force. Now, we can actually use this result to modify the work-energy theorem from what we had developed earlier. And this alternate result is what's called the alternate form of the work-energy theorem. So the alternate form of the work-energy theorem is given as follows. So first, recall from the work-energy theorem that the rate of change of the kinetic energy is equal to F dotted with Vp in I. That's the work-energy theorem we derived earlier. Suppose now that the resultant force F acting on the particle can be decomposed as F is equal to Fnc plus Fc, where Fnc is the resultant non-conservative force, and Fc is the resultant conservative force. So as a result, if we substitute that relationship in, that decomposition in, we get the following. So then, the rate of change of the kinetic energy is equal to Fnc plus Fc dotted with Vp in I, which is equal to Fnc dotted with Vp in I plus Fc dotted with Vp in I. But we already derived that the power of a conservative force is equal to minus the rate of change of the potential energy of that force, of that conservative force. So this says that the rate of change of the kinetic energy is equal to the power of the resultant non-conservative force minus du dt. Now suppose that we let E equal T plus U. And this is what's called the total energy. And it's also equal to the kinetic energy plus the potential energy. So if we substitute in, see what happens, is that then if we rearrange, we get d dt of t plus u equals dE dt, which is equal to F and C dotted with Vp and I. Now, this last result, if we rewrite it on the next line, dE dt is equal to the power of the non-conservative force. This is what's called the alternate form of the Work-Energy Theorem. And what it says is, it says that the alternate form of the Work-Energy Theorem says the rate of change of the total energy is equal to the power produced by the resultant non-conservative force. So let's write that down. So the alternate form of the Work-Energy Theorem states that the rate of change of the total energy is equal to the power produced by the resultant non-conservative force acting on the particle. Now, there's a special case of this this alternate form of the Work-Energy Theorem that arises in certain types of systems, and that's one where energy is conserved. So we're going to talk about conservation of energy. So suppose that the power produced by the resultant non-conservative force acting on the particle is 0. So in other words, what I mean by that is that, so that is that F and C dotted with Vp and I is equal to 0. So then, from the alternate form of the Work-Energy Theorem, the rate of change of the total energy is equal to 0, which implies that the energy is equal to a constant. So, the result of this is that if energy is equal to a constant, so we say that the energy is conserved if it is a constant. And note that energy will be conserved if the resultant non-conservative force acting on a particle produces no power, which is equivalent to saying that the resultant non-conservative force does no work. So as a result of that, we have this nice relationship when the resultant non-conservative force doesn't produce any power, or equivalently doesn't do any work, which is that the energy is conserved. Now, in order to be able to show how all of this works in practice, the first thing we're going to do is we're going to actually talk a little bit about common conservative forces, and then we're going to do an example. So let's actually do that now. Let's say examples of conservative forces. And then using these examples, we'll, or at least parts of these examples, will actually do a problem at the end. So one are what are called forces fixed in an inertial reference frame. So this particular type of force, I'm going to label it this way. Let F superscript I be a force fixed in an inertial reference frame I. So if that's the case, then we know then it is the case that the following is true, that the rate of change in reference frame I of this force is equal to 0. Now, the potential energy of Fi is given as follows. We're going to call this U sub I, and it's a function of the position r, where again r is the position of the particle measured from an inertially fixed point, and that's equal to minus Fi dotted with r, where again we note that r is equal to Rp relative to O, and O is fixed in I. Okay, now we know we want to show that this is actually that this is the correct potential energy and that Fi is conservative. So in order to show that F superscript I is conservative, it is necessary to show that the power produced by Fi is equal to minus dUi dt. So let's compute dUi dt. So dUi dt is equal to d dt of minus Fi dotted with r. But because Fi is fixed in the inertial frame, this is equal to minus Fi dotted with dr dt in I. So, but because r is equal to rp relative to O, and O is fixed in I, we have that dui dt is equal to minus Fi dotted with the velocity of p in I, which implies that the power produced by force Fi is equal to minus dui dt, which implies that Fi is conservative. So, an example of a force fixed in an inertial reference frame is the force of gravity, assuming that the Earth, or I could say a planet in general, more generally, is modeled as an inertially fixed horizontal plane. So in that case, the force of gravity is equal to mg, and where this is actually equal to mg times the unit vector in the vertically downward direction, and uv is fixed in the inertial frame. Of course, m and g are both constants, so they don't change with time. So in that case, the potential energy due to gravity is equal to minus mg dotted with r, where again, I'll remind everybody that r is equal to rp relative to O, and O is fixed in the inertial frame. Reference frame. Okay, now a second example is the force in a linear spring with an inertially fixed attachment. Now, recall, in this case, that the force in a linear spring is equal to minus k times L minus L naught times US, where L is equal to the length of the spring, L naught is equal to the unstretched length, of the spring. And then K is the spring constant. And then US is the unit vector in the direction from the attachment point to the particle. Now, in this particular case, we can actually start substituting the results in terms of vectors. So if we let Q be the attachment point, then L is going to equal the magnitude of the position of P relative to Q, and that US is then going to equal the position of P relative to Q, all divided by its magnitude. Now, the potential energy of a linear spring is given as, we're going to call this potential energy US of R, which is equal to K times L minus, K over 2 times L minus L naught squared, where R is equal to RP relative to Q. Now, if we want to show, so if Fs is conservative, then it must be the case that the power produced by the force in the linear spring is equal to minus dus dt. So let's compute dus dt. So dus dt is equal to K times L minus L naught times dl dt. But what's L equal to? L is equal to the magnitude of the position of P relative to Q. So that implies that L squared is equal to the magnitude of the position of P relative to Q squared, which is equal to the position of P relative to Q dotted with the position of P relative to Q. So if we want to compute dl dt, we know that d dt of L squared is equal to 2L times dl dt, which is equal to the rate of change of the position of P relative to Q dotted with itself. But that's equal to the rate of change, because that's a scalar, so arbitrarily I can take the rate of change in the inertial frame, which gives the velocity of P relative to Q in I dotted with the position of P relative to Q plus the position of P relative to Q dotted with the velocity of P relative to Q in I, which gives 2, and then I'm going to flip the order. Position of P relative to Q dotted with the velocity of P relative to Q, because the scalar product is commutative. So therefore, 2L dl dt is equal to 2 times the position of P relative to Q dotted with the velocity of P relative to Q in I, which implies that dl dt is equal to the position of p relative to q dotted with the velocity of p relative to q and I, all divided by L, but L is equal to the magnitude of the position of p relative to q, so this is equal to the position of p relative to q divided by its magnitude, dotted with the velocity of p relative to q and I. So then, the rate of change of the function us is equal to k times L minus L naught times dl dt, which is equal to k times L minus L naught times the position of p relative to q, all divided by the magnitude of the position of p relative to q, dotted with the velocity of p relative to q and I. But if you notice that the position of p relative to q divided by its magnitude, because us is the unit vector from the attachment point to the particle, this ratio of the position of p relative to q to its magnitude is actually equal to us, which implies that dus dt is equal to k times L minus L naught times us, dotted with the velocity of p relative to q and I. And that's equal to minus fs, dotted with the velocity of p relative to q and I. Now, if q is fixed in I, then we have that the velocity of p relative to q in I is going to equal the velocity of p in I, because the point from which we're measuring all distances is fixed in reference frame I, which implies that dus dt is going to equal minus fs dotted with vp in I, which implies that fs dotted with vp in I is equal to minus dus dt, but fs dotted with vp in I is equal to the power, so that implies that fs is conservative. Now, what's important about this is this step right here. This is very important. The attachment point must be inertially fixed. Because if the attachment point is not inertially fixed, then this step right here, which I've labeled with the arrow, is not true. The velocity of p relative to q and I is only equal to the velocity of p and I if the attachment point q is inertially fixed. So that's very important. That's why I started with the fact that it's a force in a linear spring with an inertially fixed attachment point. So the results of this lecture can actually be used to do some analysis on problems, and usually they're problems that have certain properties associated with them, like conservation of energy, and we can actually use these results to characterize some additional information about the system that otherwise may not necessarily be that easy to deduce. And one of the things that we can do with this is, in simple cases, we can actually derive differential equations. It's not very useful as a general tool for deriving differential equations, but in certain simple situations, it's possible actually to derive differential equations, and also to be able to make statements about whether a quantity like energy is conserved. So in order to see how this plays out, let's do an example. And this example is going to be the following problem. A particle slides on a track in the form of a parabola. Now, in order to make this tractable for what it is for the purposes of this discussion, we're going to assume that the parabola, which is the track, is inertially fixed, and there's a particle P of mass m that's moving in contact with the track. So it's moving on the on the track, and I'm going to assume for the purposes of this discussion that there's no friction and that there's gravity acting downward, and that the equation for the parabola is y equals x squared over 2b. Put this gravity over here. Okay. Now, the objective of this problem is as follows, is that in this case, we're going to be able to determine the differential equation because of the setup. But we're going to use both forms of the work-energy theorem to determine the differential equations and to be able to show that energy is conserved. So let's write this down. So the objective is use both forms of the work-energy theorem to derive the differential equation of motion and also show that energy is conserved. So how do we go about doing this? It's done as follows. Is that we're gonna set up the kinematics, and then we're going to look at the kinetics, and we're going to apply the work-energy theorem. So the kinematics in this problem, what we need to do is only up to velocity because we're dealing with energy. We don't have any acceleration in this in the results that were presented here. So because there's no rotation, we only have one reference frame. So that one reference frame is going to be the inertial frame. So I'm going to say I is equal to the inertial frame. And I didn't call it the track, even though the track is inertially fixed. I called it I for a reason, because I want to make sure that when I compute the relevant quantities that I distinguish. And remember that when we deal with contact forces applied by a track, all the intrinsic coordinates and then the contact force is expressed in coordinate system in an intrinsic basis relative to the track. So we'll get into that in just a minute, just to make the distinction clear. And in this case, though, that the setup is fairly simple, which is that I'm going to call Q the projection of point P into the horizontal, and the coordinate system that's going to be fixed in the inertial frame is going to have its origin at O. EX is going to be along OQ. EZ is going to be out of the page, and EY is going to equal EZ crossed with EX. Now from this, the position of point P relative to O, because O is my inertially fixed point, is going to equal XEX plus YEY, but that's equal to XEX plus X squared over 2B EY. So therefore, the velocity of point P in the inertial frame is equal to X dot EX plus X dot over B EY, which is equal to X dot times EX plus X over B EY. That's the velocity of point P in the inertial frame. Now, let's then compute the kinetic energy. So then, the kinetic energy is given as T is equal to 1/2 m VPI dotted with VP and I, which is equal to 1/2 m times x dot squared times 1 plus x squared over b squared. So it's important that you look back on the equation for the velocity, the inertial velocity, and see that that is in fact the case. Now we want to apply both forms of the work-energy theorem. So if we want to apply both forms of the work-energy theorem, we need to now do the kinetics. So we're going to do the kinetics next. So the kinetics are done as follows. The free body diagram of the particle is as follows. We have the force of gravity acting downward, and then we have a normal force. Now, let's characterize both of these. So N is equal to N sub N En plus N sub B Eb, and Mg is equal to minus Mg Ey. So now we have to be a little careful, okay? So because we have to make sure that we decompose these forces correctly. So we note that the intrinsic basis used in the expression for N is measured relative to the track. In this case, however, the track is inertially fixed, which implies that the track is the same as the inertial frame. So what that means is that the velocity of point P in I is equivalent to the velocity of point P in T. And remember that the velocity of point P in T is equal to the speed relative to the track times the tangent vector, where the tangent vector is the first vector in this intrinsic basis. So we can equivalently again say that that's the velocity of point P in, the speed of point P in I times the tangent vector, and ET, which is equal to VPT divided by the speed relative to the track, is the same thing as the velocity of point P in I divided by the speed relative to I. Now, the significance of that is that I can treat the track as the inertial frame when I'm doing the analysis. So when we actually get to the next step of looking at the work-energy theorem, we can see how we're going to deal with that. So we know that. Let's actually go back to this expression for the kinetic energy. So let's recall that the rate of change, that the kinetic energy, I want to go back and write that again. The kinetic energy is equal to 1/2 m x dot squared times 1 plus x squared over b squared. So the work-energy theorem, which is the first form, because I said we're going to use both forms of the work-energy theorem. So we're going to start with the basic form of the work-energy theorem, states that the rate of change of the kinetic energy is equal to the power produced by the resultant force acting on the particle. So what is the rate of change of the kinetic energy? Let's compute it. So if I take the product rule for differentiation, I get m times x dot times x double dot times 1 plus x squared over b squared, and then I get plus, and you get 1/2 mx dot squared, and then you got the rate of change of 1 plus x squared over b squared, which gives 2x times x dot, but then the 2 drops out. So we get m times x dot squared times x dot, all divided by b squared. So this is equal to, if I factor out the x dot out of everything, I get mx double dot times 1 plus x squared over b squared, and then plus m x dot squared x, all divided by b squared, where I factored out one of the x dots. So that's the rate of change of the kinetic energy. Now what's the power produced by these the forces? Well, we know that this is equal to n plus mg dotted with the inertial velocity. But remember that the inertial velocity is the same thing as the track relative velocity. So this equals the inertial speed dotted with the tangent vector. And the inertial speed is equal to the magnitude of the inertial velocity, which is equal to x dot times 1 plus x squared over b squared to the 1/2. So therefore, if we actually use this result, F dotted with Vp in I is going to equal n sub n En plus n sub b Eb minus mg Ey dotted with the speed in the inertial frame, which is the same thing as the speed relative to the track, dotted with Et. But En and Eb are both orthogonal to Et, so this gives minus mg Vp in I, and then Ey dotted with Et. So this gives that. Now let's look at Ey dotted with Et. So Et is equal to x dot times Ex plus x over b Ey, all divided by x dot times 1 plus x squared over b squared to the 1/2, which is equal to Ex plus x over b Ey, all divided by 1 plus x squared over b squared to the 1/2. So that says that the power produced by all the forces, you'll notice that in the process of doing this, we actually wind up with a with this Vp and I. So we get minus mg Vp in I, and then we wind up with Ey dotted with Et. So if I take Ey dotted with Et, notice that the only term that remains is going to be the second term, which is x over b. So we get x over b, and then Ey dotted with Ey is 1, all divided by 1 plus x squared over b squared to the 1/2. So if we substitute now in for the speed, F dotted with Vp in I is equal to minus mg, and then we've got x dot times 1 plus x squared over b squared to the 1/2, and then we have times x over b, all divided by 1 plus x squared over b squared to the 1/2, and you see the x squared over b squared, 1 plus x squared over b squared to the 1/2 cancels out, and we get the power produced by all the forces is equal to minus mg x dot, all divided by b. So that's the power produced by all the forces. So therefore, if we go back and gather up the rate of change of the kinetic energy, we have x dot times, let's go, we've got mx double dot times 1 plus x squared over b squared, and then we have plus m times x dot squared x over b squared, and that has to equal minus, and I'm going to pull out the x dot, and they've got mgx all divided by b. So then this gives x dot times mx double dot times 1 plus x squared over b squared plus m x dot squared x all divided by b squared plus mgx over b equals 0. Now you can see here that I have a product of x dot with the term in the brackets. So either x dot has to equal 0 or the term in the brackets has to equal 0. If x dot equals 0, then that means x double dot equals 0, which means there's no motion. So x dot cannot equal 0, which implies that the term in brackets is 0. So therefore, we obtain the differential equation of motion as mx double dot times 1 plus x squared over b squared plus mx dot squared x all divided by b squared plus mgx over b equals 0. And this is the differential equation. Now, what we can do is, now let's use the alternate form of the work-energy theorem. So we said we were going to use both forms of the work-energy theorem. So the alternate form of the work-energy theorem states that the rate of change of the kinetic energy, of the total energy, is equal to the power produced by all the non-conservative forces, by the resultant non-conservative force. So note that mg is a force fixed in the inertial reference frame I. So that implies mg is conservative. So if mg is conservative, then that means that the only force left is n. And n is not conservative. It's a reaction force. Reaction forces are not conservative, or normal forces are not conservative. So therefore, F and C is equal to N. And also, we have that the total energy is equal to the kinetic energy plus now the potential energy due to gravity. That potential energy due to gravity is such that UG is equal to minus mg dotted with rp relative to O, which implies that the potential energy due to gravity is equal to minus mg, so I have to be careful here, okay, so it's minus mg, so it's minus, the potential energy is equal to minus mg Ey dotted with rp relative to O. So therefore, because the negative signs cancel out, you get UG is equal to mg Ey dotted with xex plus x squared over 2b Ey, which is equal to, so what we wind up with here is we wind up with mgx squared over 2b. And you can actually see here that when we go through the analysis, that the kinetic energy doesn't change. So the kinetic energy is exactly the same as what it was before. So let's write that down. The kinetic energy is the same as before. So what does that give us? So then the total energy is going to equal the kinetic energy plus the potential energy due to gravity, which is equal to 1/2 m, and then we've got x dot squared times 1 plus x squared over b squared, and then we have plus mg x squared over 2b. And now, from the alternate form of the work-energy theorem, we wind up with dE dt is equal to Fnc dotted with the inertial velocity, which is equal to n dotted with the inertial velocity. Now you remember that I said at the beginning that the inertial velocity was equal to the track relative velocity because the track was inertially fixed. So because t is the same thing as the inertial frame, the velocity of p in the inertial frame is also equal to the velocity of p as viewed by an observer fixed to the track, but that's equal to the velocity of p in I times et, which says that n dotted with et has to equal 0, because remember that n is equal to n sub n en plus n sub b eb. So what does that say? So therefore, the rate of change of the total energy has to equal 0, which says that energy is conserved. Because remember we said that the rate of change of the total energy equals 0 is saying that the energy is constant, which means that the energy is conserved. That's because E is equal to a constant. Now, let's take the rate of change of the total energy. Rate of change of the total energy is what we have back here. So the rate of change of the total energy is equal to mx dot x double dot. Now notice these first terms are going to be the same as what we had when we computed the rate of change of the kinetic energy. Then we get plus mx dot squared, and then we get times x dot all divided by b squared, and then the last term here is plus mg x dot all divided by b. So, and that has to equal 0 because the rate of change of the total energy is equal to 0. So this results in x dot is common to all these terms. So we get mx double dot times 1 plus x squared over b squared plus mx dot squared x all divided by b squared. And actually, perhaps we can just rewrite that ever so slightly so that the m is on the outside here, plus m times x dot squared x over b squared, and then we get plus mgx all divided by b, and that has to equal 0. Now again, we notice that x dot is not equal to 0, otherwise there wouldn't be any motion, which means that the term in brackets is 0, which implies that mx double dot times 1 plus x squared over b squared plus m times x dot squared x over b squared plus mgx over b has to equal 0. Now let's compare that to what we got using the work-energy theorem. So using the work-energy theorem, we got the exact same result as what we got this time around. So this is the differential equation of motion. And what we also notice is that along the way, we were actually able to show that the energy is conserved. So we did all three. We derived the differential equation using both forms of the work-energy theorem, and we were actually able to show that energy is conserved. So the summary of this lecture is as follows. We have two forms of the work-energy theorem. The first one is that the rate of change of the kinetic energy is equal to the power produced by all the forces. The second is that the rate of change of the total energy is equal to the power produced by the non-conservative forces. And then also, we defined a conservative force. So a conservative force was defined, which allowed us to be able to construct that total energy, where a conservative force is equal to minus the partial of u with respect to r, where u of r was what was called a potential energy. And what we have in the process of that is that from this we were able to show that the power produced by a conservative force is equal to minus du dt, which enabled us to be able to construct the total energy, which was equal to the kinetic energy plus the potential energy. And then in the end, we studied an example where we showed how to bring these concepts together to analyze a problem of interest. And that's going to be the end of this lecture. In future lectures, we will use concepts from energy as necessary to be able to analyze systems and be able to see the relationships that characterize some of the key aspects of the system.